Welcome to this Mathcast. In this episode, we're going to be looking at independence versus dependence. This is a very important idea in probability. It's basically the idea that do two events, A and B, do they affect each other? And to sort of help us out with this idea, we're going to be looking at a table of data. We use tables a lot in class, and you're going to see them a lot on tests, quizzes, things like that. And so I wanted to give us a little bit of familiarity with these. This particular table looks at data of males and females and whether or not they're colorblind. One of the things that you may or may not be aware of is that males are more prevalent or more likely to be colorblind. Now, because that's the case, we may wonder if, gender and colorblindness, if those two things affect one another. Here's the data basically telling us what percentages of males are colorblind. We see that looking at it, that 5% of the males tested were colorblind versus only 0.3% of the females. And what I want to look at is I want to try to answer the following question. Are the events A and B independent? So if we were trying to make a case for A and B, event A being male, event B being colorblind, if we were trying to make a case for them being independent, we would have to be able to conclude that one does not affect the probability of the other. And if you're trying to dream up a test or come up with a way of doing that, probably the best way that you could go about it would be to look at the conditional probabilities, B given A, and also look at B given not A. Now, why would that be a good strategy? Well, if you're looking at the probability of B given A, that's going to tell you how likely someone is to be colorblind given that they're male. If you then switch out the male requirement for female requirement, if nothing changes, then that says that the event A, whether it occurs or doesn't occur, doesn't have an effect on B, and that's exactly what we're looking for. So let's go ahead and calculate both of these conditional probabilities. We'll start off first with B given A. So this is from the last podcast that we have. If you need to review conditional probability, feel free to go back and check that. But this is our formula for conditional probability. The probability of B and A would be the intersection of A and B here in the table, which is 0.05. And the probability of A is the total of that column, which is 0.5. If you divide the two, you'll get 0.1. So the probability of someone being colorblind, given that they're male, according to the data, is roughly 10%. Right, if we change this over to female instead, the formula in this case looks like this. And the probability of B and not A, or colorblind and female, is 0.003 in this case, much lower. But notice that the percentage of females remains exactly the same. Because of that, it's clear that changing from male to female made a difference. In other words, the occurrence of A had an effect. On the probability of B. Now, taking sort of all this into stride, really what you're after if you're testing for independence and dependence is the following idea. You should always have that the probability of B given A equals the probability of B given not A, and both of them should be equal just to the probability of B. In other words, you shouldn't have conditional probabilities when you're working with independent events. They shouldn't be conditional on one another at all. So this is really the test for independence and dependence that we'll want you to remember throughout the rest of the semester. This actually plays a big role in statistical studies, and although we're not going to go that far into the idea of independence and dependence from a statistics point of view, it is good to at least get a feel for it now. All right, thank you for watching.